refractive index, and this is from the CBSE standard 10 syllabus. In my previous videos we have discussed about refraction through glass slab. If you have any doubt regarding refraction phenomena, then please refer my video and then come back to this topic. So this topic is the refractive index, a ray of light that travels obliquely from one transparent medium to another will change its direction in the second medium. Now we have seen that if this is an interface of the surface, that means from here another medium is starting and here the medium is there. So this we are referring as medium 1 and this we are referring as medium 2. Now suppose this is a medium air and this is a medium glass, that I am taking example of refraction through glass slab. Here we have seen that if this is a normal is a perpendicular to any surface. So when a ray is coming obliquely from one medium, so this is air and ray is coming obliquely. Obliquely means a slanting. So when a slanting or oblique ray is falling on the surface of one of the medium and it is passing through this and it is going to travel in the second medium. So what will happen? We have to see the density difference between these two medium. If this medium is rarer, and this medium is dense, now it is always comparable that whenever you have two mediums with you, one medium will be denser and one medium will be rarer. For example, we are taking air and glass. Into that, air is a rarer medium and glass is a denser medium. Whose density is more will become denser medium. Now when we are taking air and water, so water will become denser and air will become rarer. But water is denser because other medium is air. If we are taking water and oil, then water will become rarer and oil will become denser. So it is always relative that which two medium you are comparing with each other and which two medium the light is passing. So here when it is coming from rarer medium to denser medium, it will bend towards the normal like this because its speed will decrease. Here the speed is more and here the speed will decrease because it is denser medium. And again when it is going out from the denser medium to rarer medium, here this is a normal. If this is a normal here, then it will move away from the normal like this because again its speed will increase. It is when it is going from denser medium to rarer medium. So this is a refraction when light will bend because it is traveling in another media or it is just changing its medium. So it will bend. This refraction is happening because light is changing its medium. Either from rarer to denser or from denser to rarer. Now it will move towards the normal or it will go away from the normal. That is depending upon is it coming from rarer to denser or from denser to rarer. But the phenomena of bending of the light is known as refraction. So both the ways it is refraction. So here a ray of light that travels obliquely from one transparent medium, any transparent medium, into another. So either it is from this to this or this to this. Into another will change its direction in the second medium. So that is refraction and the extent of change in direction that take place. Now we know that it will get refracted, it will change its direction. That from here to here or from here to here it is changing its direction. But how much it is changing direction, that measure will give us refractive index. So whenever we are checking that how much it has bent or how much it is going to bend, so that we can measure it through refractive index. The extent of change means how much change will happen in the direction that take place in a given pair of media. It is always a pair of media. There will be always a two media. One will be rarer medium and one will be denser medium. May be expressed in terms of the refractive index. So what is a refractive index? That how much light has bent, that extent, that measure or that physical quantity is our refractive index. Now light is traveling fastest into the vacuum and its speed in the vacuum is 3 into 10 raised to 8 meter per second. Now into the air the speed is marginally less, so it is almost equal to vacuum only. So in air also we are taking light speed is equal to 3 into 10 raised to 8 meter per second. Actually if we are going into the physical quantity then it is little less compared to this, but it is almost equal to this. So we are taking the speed of light in air also this. Now this speed is very less in water and into the glass. Now let us derive the formula of refractive index. So here we are going to derive formula for the refractive index. So here we are taking ratio of speed of light in medium 1 divided by speed of light in medium 2. So that ratio will be our refractive index, and that we are representing with n. So here two medium are there. This is air medium and this is glass medium. So from air the ray is obliquely falling on the surface of the glass and it is passing through the glass slab. These two mediums are there, and here this is I. I means angle of incidence, and here R means angle of refraction. How much ever it is refracting, that we can see it from the angle of refraction, and here angle of incidence. This is incident ray and this is refracted ray. Now when we are taking a ratio of these two, then speed of light we are considering in medium 1 is V1, whereas speed of light in medium 2 we are considering as V2. So first we are taking a ratio of V1 by V2. So in the numerator we are going to write the speed of light in medium 1, and that is going to be V1, divided by we are taking speed of light in medium 2 equals to V2. Now this is our refractive index. So here what we are doing is we are checking the refractive index of medium 2 with respect to medium 1, because ray is coming obliquely and that is falling over here on this surface and then it is going to bend. So actually we are going to find here the refractive index of glass medium, that when ray is coming through the air, how much it is bending. So actually this ratio is for the finding refractive index for the second medium, and that is glass medium. Here it is not bending because that medium is air, and even if it is bending, we are checking that with respect to this ray, that this ray is our reference ray, and compared to this ray, how much this ray has got refracted or it got bent. So that we are finding here. So speed of light in medium 1, that we are taking as a reference, and we are finding it the refractive index for the medium 2. So refractive index 2,1 means we are finding for the second medium with respect to medium 1. So that is our ratio for the medium 1 divided by medium 2. Now in second case, when we are finding out the refractive index for the medium 1, that if we are taking this ray OB as our reference ray, then that will come into the numerator, that speed of light in medium 2 equals to V2 divided by speed of light in medium 1 equals to V1. Now here the opposite thing we are doing, that with respect to this ray, we are finding out the bendness of the second ray, that with respect to this OB ray as a reference ray, we are checking that how much this OA ray has got bent. So that is V2 divided by V1. So refractive index here, that we are taking a reference medium 2 and we are finding for the medium 1 that how much it is bent. So this is a refractive index 1, 2, that is speed of light in medium 2, speed of divided by speed of light in medium 1, that is V2 divided by V1. So these are the general formulas when we are checking and when we are making one of the ray a reference ray, because otherwise we will not be able to find out that how much that ray has got bent. If we are checking that this line is slightly slanting, then how you will check that how much it has slant? With reference to one of the line which is straight. That we need always a reference to check that how much this line is slanting. So like that, one of the ray, when we are comparing two medium, one of the ray we have to make a reference to check the other ray has got how much bending or how much it is bending when it is passing through that. So when you are finding for this, we are making this as a reference ray, or when you are finding for AO, you are making OB as reference ray. And that is how it will work for the refractive index. Now let us consider our one of the medium is air, and that is fixed because we are taking air as a medium where the light speed is maximum and there it is not bending. It travels straight through the air. So one of the medium when we are taking air, and with respect to air when we are checking a different mediums like glass, water, oil, and when we are taking this two comparison, that air with respect to all the other medium, then that refractive index is known as absolute refractive index. When we are checking any other medium with respect to only air, that refractive index is known as absolute refractive index. So in our syllabus, whatever refractive index we are studying are absolute refractive index, because we are always going to calculate the refractive index of any medium with respect to air. So all the absolute refractive index in general will known as refractive index. Now let us write the formula for the absolute refractive index or refractive index in which one of the medium will be air. So this is our refractive index or absolute refractive index in which we are taking speed of light in air divided by speed of light in any medium. So here we are taking any medium like oil, water, glass, any medium. So here speed of light in air is c, whereas speed of light in any medium we are considering as a v. So we know that speed of light in the air is 3 into 10 raised to 8 meter per second and divided by v, and here refractive index will be there. So based on this formula, we are going to solve many problems in which one of the thing will be given to you. We know this. So we can find out either the refractive index of the medium or we will find out the speed of light in that particular medium. Refraction by spherical lenses. Earlier we have studied the reflection by the spherical mirrors. So these cases are almost similar to the mirrors. Only thing which makes these cases different than the mirrors, that here there are two surfaces which are giving us refraction, whereas into the mirrors there was only one surface which was giving us reflection. So if we are drawing a convex mirror, this is a convex mirror because one surface is painted and only one surface is a reflecting surface. So whatever ray will fall on that, it will reflected at certain angle, that is a refractory angle. So this is having only one surface which will give us reflection, whereas here this is called a double-sided lens because at both the side it will give us refraction. Here the light source is here towards the left hand side. So that's why all the parallel rays are falling on this convex lens. And we are getting the result towards the other side. But if I have kept the light source towards right side, then the similar result I will get towards the left side, because it has two surface which will make it convex lens. So here it is something like this, that this surface and this surface. If we are making for the rays from this side, then we will get the result towards this side, that all the rays will get collected at one point. If we are keeping the light source towards this side, then all the rays will get collected at the one point towards this side. So it has two surfaces, two spherical surfaces. So this makes them a double convex lens. Simply we are calling it convex lens. And similar thing will happen when we are talking about concave lens. So concave mirror is like this. This surface is being painted, so we are using this surface for the reflection. So this is concave mirror. Similarly, we are attaching two surfaces of the concave lens, and this is going to be a double-sided concave lens. So here this surface is also we can use, and this surface also we can use. So this is concave lens and this is convex lens. So these are the lenses and these are the mirrors. In mirror we have only one surface, and those two mirrors are giving us reflection. Whereas here these are the lenses and they have two surfaces and they are giving us refraction. Refraction means light will bend because it is passing from the glass. So those phenomena we are going to study when we are going to study the refraction through the spherical mirrors. Our lenses are part of spherical mirror. So this is our convex lens, and if we are talking about this surface, then it is a part of sphere which is lying towards the left hand side, and its focus point is here and its center of curvature is here, which is a middle point of the sphere. So this is going to be C1 and this is going to be F1. Similarly, when we are talking about this surface of the lens, then its sphere is towards this side. It is a part of sphere which is lying towards the right hand side. So it also has a focus point and it also has center of the curvature, that is C. So this F and C we are giving name F2 and C2. So the lenses are having two focus points. That means they are having two foci. It is a plural form of focus points. So they are having two foci and two center of the curvature, because they are part of two different spheres and we have made them joint and we have made this convex lens. So this is a convex lens and that's why it is known as double convex lens, but simply we are calling convex lens. The similar thing will happen with concave lens, that it is something like this. Now this surface is a part of sphere which is lying towards the left, and this surface is a part of sphere which is lying towards the right. Here it will be opposite. This surface is a part of this sphere and this surface is a part of this sphere. That's why convex lens focus point and center of the curvature is lying behind the mirror, that we have studied in reflection of the mirrors. But here into the concave lens, it will lie in front of the mirror. So that's why they are part of the sphere which are lying in front of them. So here whatever we are getting is, and here whatever we are getting is F2. Similarly, the center of the curvature will be C1 and the center of the curvature will be C2. So both convex lens and concave lens both are having two foci and two center of the curvatures. Now let us understand that when parallel rays are falling on the convex lens and concave lens, what type of results we will get. So when parallel rays are falling on the convex lens and concave lens, these are the results what we are getting. And that is why the convex lens is also termed as converging lens and the concave lens is also termed as diverging lens. when the parallel rays are falling on the one of the surface of the convex lens. So after refraction, those all rays are converging at one point, and that point is known as principal focus of this convex lens. And this is a optical center of the convex lens, and this is the optical center of concave lens. So the middle point, so the center of the lens is known as optical center. So here O is optical center for convex lens, and this is O for the concave lens. So here when the parallel rays are falling on the one of the surface of convex lens, all those rays are converging at one point, and that is towards the other side of the lens, and that is known as principal focus of convex lens. When all the parallel rays are falling on the surface of the concave lens, all those rays are getting divergent action. So they all will diverge in all the direction, but when we are extending those rays towards the back side, then at one point they all will meet. That point is known as principal focus of concave lens. So this is the difference in convex lens and concave lens. Earlier we have seen that in convex mirror and concave mirror. In convex mirror we have seen that whatever rays were reflected, we are tracing back them and we are checking the focus point and the center of the curvature of the mirror. But here that action is reversed, that here we are getting it at the other side, because this spherical lens sphere is lying towards this side, and this spherical lens sphere is lying towards this side. So accordingly we will get principal focus towards other side and towards the same side. So here when the rays are falling on this surface, then in convex lens the principal focus will be the other side, whereas here when rays are falling on this surface, the principal focus will remain on the same side. That is the difference when parallel rays are falling on them. Other thing, that when the parallel rays are falling on the convex lens, it will collect all the rays. So that action is known as converging action. So convex lens is showing converging action, and that's why it is known as converging lens or converging lens. But here the convex lens is showing the diverging action. It diverges all the rays. It spreads all the rays in all the direction. So that action is known as diverging action, and that's why this lens, concave lens, is also known as diverging lens. Refraction by the convex lens, and here we are going to discuss the nature, position and size of the image when we are keeping the object at various places in front of the convex lens. So here first we are checking that when parallel rays are falling on the convex lens, at that time all the rays will get collected at one point towards the other side of the convex lens, and that point is going to be the focus point of this convex lens. Now if you have any doubt about what are the convex lens, how many focus point they have, and what all are the center of the curvatures for the convex lens and convex lens, then please refer my previous video and then come back to this video. It will be much easier to understand all this terminology. So first case, what we have already discussed this in that video, that when parallel rays are falling on the convex lens, it shows the converging action, that it collects all the rays at one point, and that point is going to be the focus point of the convex lens. Now second case, here in the mirror and in the lenses we are following the one thing to check the nature and size and position of the image, that we are starting from the infinity, that these rays are coming, that these rays are parallel, but these rays are coming from the infinity. So from the infinity rays are coming, so we are keeping object at infinity, so we are getting all the rays collected at one point, that is F2 focus point. In second case, we are taking it little bit closer. Now this is the first case in which we are keeping the object at infinity. Then we have in between C1, F1, then optical center. All these are the points in between the pathways from, all these are the points in front of the convex lens. So here first case we are taking that we are placing the object at infinity. Then we are placing the object near to the center of the curvature. So in between infinity but towards the center of the curvature, and it is known as beyond C1 or it is beyond center of the curvature. So this is going to be our second case. When we are keeping the object over here, which kind of image and what size of image we will get. Then third case we are taking that we are keeping object at center of the curvature, that is C1. So this is going to be our third case, that slowly we are going towards the optical center. So here we are keeping our object. So we will discuss that where we will get the image and how we will get the image. Then in next case we are going to keep the object in between center of the curvature and focus point here. So that is going to be our fourth case. So that is here. Now fifth case is we are going to keep object at focus point. So that is going to be our fifth case, that when we are keeping the object at focus point where we will get the image. And the last case, and that is the sixth case, that when we are keeping our object in between optical center and focus point where we will get the image and how we will get the image. So these 6 cases we have discussed when we were studying the concave mirror, and we have seen all these 6 cases for concave mirror. Here we are going to discuss all these 6 cases for convex lens. So here I have shown the 4 cases, and after this we are going to study the 5th and 6th case. So let us start from the first one, which we have already discussed, that when the objects are at the infinity and all the parallel rays are falling on the convex lens, we will get a focus point, we will get image at the focus point. Then second case, when we are keeping the object beyond C, beyond center of the curvature, or we can also say in terms of lenses that this is 2f1. This is first focus point and this is second focus point. But here we are going to maintain it C1 so that we will not get confused in between 2f1 and f1. So this is going to be our center of the curvature 1 and this is going to be our center of the curvature 2. So when we are keeping the object beyond C1, there will be 2 rays which will give us image towards the other side of the lens. Now it is not going to happen that only 2 rays are coming out from the object. There will be many rays, but to see the diagram clearly and to see the action of the rays, that how they are falling on the lens and how they are getting refracted, to see that we are mentioning only 2 rays. And these 2 minimal rays will give us idea about that where we will get the image and how we will get the image. So here this is an object, AB is an object. This is object here, and that we have kept it beyond C. It is not at the C1. It is beyond C1. So far from the C1, and it is not towards the lens. It is just far from the lens. So it is beyond C1, and when the rays are passing through the lens, one ray will just pass from the optical center. When any ray is passing from the optical center, it is not going to refract. It is not going to bend. It will choose the straight path and straight ways it will just go out from the lens. So this ray will be straight rays. So another ray which is coming out from the object, that is getting refracted here, and that is meeting this another ray which is passing from the optical center over here, and that position is in between focus point and center of the curvature. The second focus point and second center of the curvature, that is other side of this lens. So in between these 2 we are getting the image, and an image is A dash B dash. The image is diminished and image is real and it is inverted. It is upside down image. Then in third case, when we are keeping the object at C1, that AB object we have kept at C1, so we are getting the refracted image over here, and that is at C2. So when we are keeping object at C1, the other side of the lens we will get the image, and that is C2. It will be of the same size, real and inverted. Now in fourth case, when we are moving towards the F1, so we are keeping our object in between C1 and F1, in between center of the curvature and focus point. At that time we will get the image beyond C2. That means we are getting the image beyond center of the curvature, and that is the other side of the lens. So we are getting the image enlarged, that is very big compared to our object, real and inverted. So in all these cases we have seen that we are getting the inverted image. In this case we are getting the diminished image. In this case we are getting the same size image, and here in this case we are getting the bigger size image compared to the object. So here we can note down like this, that when we are keeping object at this different position, we are getting image at all this location. That when we are keeping the object at infinity, we will get the image at F2, and it is highly diminished. Whereas when we are keeping the object at second, that is beyond C1, we will get the image in between F2 and C2. When we are keeping the object at C1, we are getting the image at C2 and same size image. When we are keeping the object in between C and F, we are getting the image beyond C2, and the image will be enlarged. In all of this case, we are getting the image real and inverted. All of these cases we are getting image real and inverted. So when you will remember like this, it will be easy for you to discuss each and every case, and you can also remember that what will be the nature and size of the image. Now let us discuss the last two cases, that when we are keeping the object at F1 and we are keeping the object closer to the lens. So our fifth case is when we are keeping the object at F1. At that time we are getting the image at infinity, and that image is going to be highly enlarged and real and inverted. So when we are keeping the object at F1, we are getting the image at infinity. So here I am going to mention 5, and here I am going to write at infinity and highly enlarged. Now last case, when we are keeping the object beyond F1 or towards the convex lens, that is in between focus point and optical center. When we are keeping the object AB, we are getting the image towards the same side of the convex lens, and it is going to be virtual and erect. So towards the same side we are getting the image over here. That sixth case is there, and when we are keeping it over here, we are getting the image after C, that is center of the curvature, and this is C1, that center of the curvature 1. After that we are getting, but we are getting towards the same side. So for here the image is, for the sixth case, the image we are getting it over here. It will be enlarged, virtual and erect image. So all these are the cases that when we are keeping the object at all this position, we are getting the images like this. So all of these cases, for the real and inverted, only this we are getting virtual and erect. So let us understand all the cases like this. All these black numbers suggested that these are the position of the object, that when we are keeping at the infinity, so we are getting image at F2 and it will be highly diminished. When we are keeping the object beyond C1, we are getting in between F2 and C1, it will be highly diminished. Then when we are keeping the object at C1, we will get the image also at C1 towards the other side, and it will be same size. When we are keeping the object in between C1 and F1, we will get the image beyond C1. So that will be enlarged. When we are keeping the object at F1 position, we will get the image at infinity, it will be highly enlarged. And when we are keeping the object in between f1 and optical center, that case will be the sixth case, and we will get the image towards the same side, and that will be towards the beyond C, and that image will be enlarged, virtual and erect. So for the case 1, 2, 3, 4 and 5, all the images are real and inverted. And what will be the size of the image? That for the first case it is highly diminished, then it is same, enlarged and highly enlarged. So from the point size it is growing bigger, and at the last it is virtual and erect. And sixth one is virtual and erect. So if you will remember like this, all the cases for the convex mirror, it will be very easy for you to remember that what all are the position of the object, what all are the position of the image, and nature and size of the image. Now we are discussing two cases for the concave lens. That first case is when we are keeping the object at infinity and all those rays are falling on the concave lens. Those rays, when we are extending towards the same side, we will get the image at focus point f1. So this image is highly diminished and point size, and it will be virtual and erect. Whereas in the second case, when we are keeping the object in between center of the curvature, that C1, and in between f1 and C1, we are getting the image that is in between focus point and optical center, and that image is also virtual and erect, but it will be highly diminished. So it is very small size image, as we can see that the size of object compared to the size of object, that image size is very less, and it is going to be at the same side. Here also the image we are getting at towards the same side. So from the convex lens and from the concave lenses, we are getting the images from that convex lenses images, we are getting the other side of the lens. Whereas in the concave lens, we are getting the images towards the same side of the lens. Image formation using ray diagrams, and that too in convex lens and concave lens. If you have any doubt regarding concave or convex lens, then please refer my video about basic information about the lenses and then come back to this video. So here two cases we are discussing for the same parameter. That one case for the convex, one case for the concave, in which the incident ray we are keeping it same, but we will see the pattern of the lens, that how that ray will get refracted, and after that where we will get the emergent ray. This is a refraction, that light ray is bending, that is a refraction. So we will say after refraction we will get a ray that is called emergent ray. This is an incident ray, ray which is falling on the lens, that is incident ray. This is a refraction which will happen within the lens, and because of that the light ray will bend, and then whatever ray, the resultant ray we will get, that ray is known as emergent ray. So same incident ray when fall on convex and concave lens, we will see how the results will differ because of their design is different and because of their refraction pattern is different. So first case is this, that when the parallel ray is falling on the lens, that ray is parallel to the principal axis. Here this is a principal axis which is passing from the optical center of the lens. That is a straight line. This is the optical center. Optical center is a midpoint of the lens. That is an optical center. This f1 and f2 are two foci of the lens, because lens are double convex lens and double concave lens, because both the surfaces will give us refraction. So that's why they are having two foci and two center of the curvature. So in first case, where we are taking incident ray that is parallel to principal axis, PA is suggesting principal axis. So as a resultant ray or as an emergent ray, after refraction, that ray will pass from the principal focus here to the other side and here towards the same side. But at both the lenses, we will get the ray that will pass from principal focus. So here this action shows us that this lens is converging lens and this lens is diverging lens. So that's why it diverges all the rays. But when that emergent ray we are extending towards this side, we will see that it is passing from the focus point. So in both the cases, the emergent ray is passing from the principal focus, but in the convex lens it is passing from the principal focus from the other side of the lens, and here it is diverging away, but when we will extend that ray, that will pass from the same side of the principal focus. Now in second case our incident ray is passing from the principal focus and then it is getting refracted from the lenses. So the emergent ray will be parallel to principal axis. Here, now this is a reverse situation of the case 1, that here incident ray is parallel to principal axis and then emergent ray is passing from principal focus. Whereas here incident ray is passing from principal focus and the resultant ray will be parallel to principal axis. So here this is incident ray which is falling on the lens, and then after refraction it will just emerge as a parallel to principal axis. Here the ray is falling on the lens, after refraction it will emerge as parallel to principal axis. Then third case, in that incident ray is passing from the optical center, then emergent ray will be emerging without deviation. So when any ray is passing from the optical center, it will go straight and it will not get any kind of deviation, because this is the one point in the lens which will not refract any ray. So these are the three different cases which we have seen for the both convex and concave. The lens formula and magnification, and we will see that how the lens formula and magnification for the lens is different from the mirror formula and magnification for the mirrors. So here lens formula is 1 divided by V minus 1 divided by U equals to 1 divided by F. Now here V is image distance, whereas U is object distance, and F is a focal length. So what is a focal length? Focal length is a distance from the principal focus to the optical center of the lens. So that is known as focal length. So here this is a lens formula, and for the magnification we have H dash divided by H. So H dash here is a height of the image, whereas H is a height of object. So this ratio will give us magnification, and height means how much tall or what will be the size of image and object. Here we can refer this height as size also, or how much tall object or how much tall image we will get. Now other magnification formula is V divided by U, whereas V is a distance of image and here distance of object. U is distance of object, and this distance we are calculating from the optical center till the image or optical center till the object. So this is V by U. Now these are the three formulas. These two formulas are for the magnification and this formula is for the lens formula. That where we will get the image and what type of image we will get, that we will get to see from the magnification. Now let us see that how these formulas are different from mirror formulas. Now these are the differences between mirror formula and lens formula. That here 1 divided by V, here plus sign is there, then 1 divided by U equals to 1 divided by F. Whereas here the negative sign is there. whereas V is a distance of the image, U is distance of object, and F is focal length. Magnification formula is H dash by H, where minus V by U is there. H dash and H refers to the height of image and object respectively. Here also the same formula will be there, but when we are taking the distance of the image and object, this will be plus and this will be minus. So in this formula it is plus, but here it is minus, whereas here it is minus, and here this quantity this terms we are taking plus. So that is the basic difference between mirror formula and lens formula. But rest all Cartesian rules will remain same here. That if we are getting the distance of the image or distance of the object here in this region, then it is going to be negative. Also, if we are getting the answer in negative, that means they are over here or they are towards the left side of the lens or of the mirror. Now, if we are getting the positive answer, then image or the object both are lying over here. If we are getting the answer in positive. So this is towards the left side and this is towards the right side. So if positive answer is there, that means they are towards the right side. If negative answer is there, that means they are towards the left side for the distance of image and for the distance of object. The same way we are checking for the principal axis above and below. If it is above the principal axis, we will get the image. Then the answer is going to be, then it is going to be positive. Where we are getting the answer negative, then it is below the principal axis. And if it is below the principal axis, that means the image is inverted. Object can never be inverted. So that is definitely for the image, and that will be inverted, because always you are getting the image like this. It will be never upside. It will be always upside down. So that is always upside down, and below it will be inverted only. So these rules will remain same for both of these formulas. Only this sign will change for mirror and lens, and that too in magnification it changes only for the distance, and for the height and size it will remain same. So the ability of lens to converge or diverge light ray depends on its focal length. Now what is the meaning of convergence and divergence of lens? That we have already learned, and that is when this is a convex lens. When parallel ray will fall on that, it will converge a light rays. So all the light rays, what all will fall on that, it will converge and all the rays will meet at one point. That will be the focus point. Now divergence means when a concave lens we are using and all the rays will diverge away like this. What all parallel rays are falling on the concave lens will diverge away, and how much they will diverge away or how much they will converge, that will depends on its focal length. The degree of convergence or divergence of a light rays achieved by a lens is expressed in terms of its power. So in short, how much it can bend a light or how much it can converge or diverge a light, that is depending upon the power of the lens. So here convergence we can see it in convex lens, and divergence we can see it in concave lens. But how much they are bending a light or how much this phenomena they can show us, that is depending upon the power. Now power is reciprocal of a focal length, so that P equals to 1 divided by F. So when we are taking a reciprocal of a focal length, we will get a power. Now let us understand more about the power and the units of the power. SI unit of power is dioptre, and we are writing it with capital D. So D is dioptre, and that is a unit of the power. Now 1 dioptre we can define it like the power of a lens whose focal length is 1 meter. it can be convex or it can be concave. If its focal length is 1 meter, then its power is 1 dioptary. So that is how we can define 1 dioptary of a power. So that also means that 1 capital D, that means 1 dioptary equals to 1 meter inverse. Now why this meter inverse is there? Because earlier we have seen that D equals to 1 divided by F. So F is in the denominator, and that's why focal length will come in the denominator, and that's why that is meter inverse. So 1 dioptary equals to 1 meter inverse. Now power of convex lens is always positive. So whenever we will say that plus 2 D power is there, that means that lens is a convex lens. And if the power of lens is negative, then it is a concave lens. Convex is the lens which is bending outward, and concave is the lens which is bending inward. This is a convex lens and this is a concave lens. Now let us see one example, that if the power is plus 2.0 D is there, then what will be the lens and what will be the focal length? So lens we can check from the positive or negative sign. If it is a positive, then it is convex. So lens is convex. And what will be the focal length of this convex lens? Then P equals to 1 divided by F. We can also write that F equals to 1 divided by P, and that's why we will get 1 divided by 2. So when it is 1 divided by 2, we will get 0.5 meter. So this is our quotient. With quotient, it is only meter and not the meter inverse. So our focal length is 0.5 meter. So the lens whose power is plus 2D, that lens is a convex lens and its focal length is 0.5 meter. So hope this video has cleared your doubt. In coming segment, we are going to discuss many more important concepts. So don't forget to subscribe, learn yourself. I'll see you in next video. Till then, keep learning, keep sharing.